In this video, I consider this to be probably the most important and misunderstood aspects of oscilloscopes, and this is triggering. It is the most important feature of any oscilloscope, and it's no different for the PicoScope. We're going to look at triggering from a threshold perspective, and we're only looking, although there are many different types of triggering methodologies in the PicoScope, we're only going to look at simple edge in this because it's quite a complex area to look at, and so I don't want to make things overly complicated, so we're going to just look at this from a simple edge perspective, which will actually introduce the concept of triggering. But if you understand this and you want to have a play, then have a play. You know, all engineers learn by playing, so maybe you can set up your own experiments and play with this, but we will do other videos on the different types of edge triggering. But what's important, this one is just to get you started, to give you an idea of what triggering is all about. So we're going to look at simple edge triggering. We're going to look at the triggering modes, whether it be classified as no triggering, normal triggering, auto triggering, and single shot, and they all have particular reasons for being used. We're going to investigate triggering through experimentation, and so I'm going to look at it from an analog perspective, where we're going to look at RC networks and see how thresholds can be used to actually perform experiments and analyze the charge discharge characteristics of capacitors. We're going to look at it from a digital perspective in a very simplistic communications format, which is using SPI. Now, many of you may not understand what SPI is. That's serial peripheral interface. It's a very common protocol that's used, but this is not about trying to explain the protocol in detail. This is just using it as a means to an end to explore triggering and how to look at more complex events that occur. And so we use that as an experiment. And also, finally, we also look at a very interesting aspect, which is switch bounce. And it's actually a sort of like a random event. And you wouldn't believe how noisy switches are. You'd think they just go on and off, but they don't. They have switch bounce, and it's discussed as a parameter within switch design. But it's actually really interesting to see it from a scope perspective and actually see how long switch bounce can actually go on for. And so I just do a very simple experiment looking at that. So I hope you enjoy this one. It's quite an interesting set of experiments. So yeah, hope you get on well. So let's have a look and see where we start. So what is triggering and why is it so important? Triggering is the term used to define the way in which an oscilloscope will capture and display a waveform. Normally, an oscilloscope is in its with no triggering at all, is just scanning and displaying the signal. And we will see that in detail shortly. But sometimes you actually want to lock a signal so that you can actually see it in more detail. And this is where triggering comes in. And without it, we would never really be able to observe most of the signals that we look at in terms of analog systems, looking at phase relationships, looking at protocols and all that kind of stuff. So it is so important, okay? So triggering allows you to do the following. Capture a specific waveform event through its characteristics, i.e. its threshold, its direction, and the trigger type. Now we're going to look at all of these elements, and we're only going to look at the simple edge trigger type because I want to get you started, and it's the easiest way to understand triggering. There are much more complex forms of capturing signal or waveform characteristics, which the PicoScope is perfectly capable of doing, but it requires a lot of setup to get to be able to demonstrate those, and it's not relevant at this particular point in time when you're only just learning about triggering. But once you do understand this, then go and play, which is the greatest thing that engineers go off and do. The more you play, the more you learn. But anyway, let's see what else have we got. It allows you to stabilize the waveform on your screen. And this is where you'll see terminology as auto, normal, and single mode. And we're going to go through each of these in turn so that we can see exactly what they do. Automate the capture of a waveform event, and this is where the auto and normal come in, so that you don't have to do anything, it sits there and does it for you, but it's important to understand the difference between the auto or the normal modes. Capture a waveform event when you're ready, and this is really important. Quite often you just want to see a single event and then you want to examine it in detail. Whereas if these events are going off all the time, then you're thinking, hang on a minute, I just want to see what I just saw, not what I'm doing now. So this is where single mode comes in, and we'll talk about that. And we're going to show this through circuit examples. Okay, so it's quite exciting, really. and in this one, examine the captured event in detail from a time perspective. And we're going to do all sorts of experiments to try and demonstrate all of this. But the final experiment we're going to do in this tutorial is actually looking at switch bounce, which is a really good example of capturing an event and then looking at what's going on from a time perspective. Okay, but it really applies to most signals like capacitors charge and discharge and all that kind of stuff. So, but we're going to go through these experiments and be able to see all of this in detail. And observe waveforms in detail relative to each other. Now, this is really important if you're looking at phase relationships, whether it be analog or digital. And so if you've got a trigger event on one channel, you can observe a signal relative to another channel. And that's really, really important when you're trying to set up things like quadrature encoding or something like that, which some of you may not know what that is. But it's about digital waveforms in phase relationship with each other. And it's really important to actually be able to analyze these to be able to set systems up. So, and this is once again why triggering is so important. And also you can perform pre and post signal analysis, because triggering allows you to see what is happening before an event and also after the event, and it also allows you to move in time through an event. And these are all the powerful aspects of triggering. Okay. So let's see what's next. So triggering features. So what I want to do is just discuss triggering threshold first, okay? And the question about triggering thresholds is what voltage. The trigger threshold is the transition, the voltage transition that a signal goes through, and whether or not the system is set to a particular voltage to capture an event. So this suggests that in order to catch a signal, the trigger threshold must be within the region of the signal voltage itself. If you had a digital signal that was going from 0 to 5 volts, then your trigger voltage must be between 0 and 5. And it would seem to make sense to set it somewhere halfway. Similarly, you might have a a signal which is an analog signal going around 0, like a sinusoid that goes around 0. It doesn't necessarily have to go around 0, but say, for example, it does go through 0, in which case your triggering threshold would need to be 0, or somewhere within the amplitude of the waveform. So if it was 5 volts peak to peak, so that's 2.5, for example, plus 2.5, minus 2.5, if it's going through 0, then any voltage between that range will allow it to trigger. But if you go outside of that voltage of the signal, it can't find the trigger, and therefore it won't trigger. And so the threshold voltage is really, really important. And this is about analyzing and understanding signals. And this is why I say to you about using oscilloscopes, is it's important to understand what you're looking for in order to set oscilloscopes up. And yes, I know there's auto features. I know if you've been watching other videos, you know I'm not overly keen on auto features because it doesn't educate you and you're not in control of your test equipment. I would rather you were taught about being in control of your test equipment so you can get it to do what you want it to do, not what an auto feature will allow, try and do for you, okay? So it's better to do as everything from a place of knowledge, okay? So that's just to give you a rough idea what threshold means. And we'll talk about that when we actually set up our experiments. So we're going to look at triggering types. We're looking at this simple edge, although there are many variants of this. And this video is purely about looking at edge triggering. You can have window triggering, you can have all sorts of triggering, but I don't want to complicate this more than necessary, and we are only looking at simple edge triggering. So I will show you that when we look at the actual triggering modes. And then we come into triggering modes, and there are fundamentally 4 modes. There's no triggering, there's auto triggering, normal triggering, and single shot. And we're now going to look at this in detail. Okay, so let's go to our PicoScope. Now, what we have here, I've set this up. I've got a signal generator. which you'll see a signal every now and again as I'm talking. This is really important that you actually see this. So I've got a signal which is a 1 kilohertz signal, is 1 volt peak to peak, but I've put the signal generator into burst mode, so it only does one cycle once every half second. And I've set this up, one, because if I do it any slower than this, you may not see it, because when I'm doing screen capture and running the PicoScope at the same time, you don't always see, see the signal because of the delays between the two systems, because my laptop is doing a lot of processing. So I have set my, if I go to channel A here, my probe is on times 10, I think. And yes, it is. So I know the signal what I'm getting here from my signal generator. So it's 1 volt peak to peak. So I've set my scope for plus or minus 1 volt. So I know it's captured, and this is running around 0 volts. So there's no offsets here. It's DC coupled, which is fine. And I've got it in manual mode, which is great. And so so if we now look at the, from a time-based perspective, I've also set it to 1 millisecond, which allows me to capture a 1 kilohertz waveform quite easily and visually see it, as you can actually see it flashing up on the screen. So now let's go to the trigger, and we're in none. And the type, I mentioned this type earlier on in the when we were just discussing the different elements of triggering. And I just want to say to you that there are all these different, there's advanced edge, window, interval, pulse, etc., etc. We will do other videos on these, but they require a lot of setting up to actually demonstrate these, and this is not necessary at this point in time. To get you started, the only one you're interested in is the simple edge, and this is what it generally defaults to, okay? And that's what we're going to discuss. Now, if you're in no triggering, then obviously it doesn't matter what the source is. The pre-trigger, we'll discuss these later on. But if there's no triggering, there's no threshold. And so what you're seeing on the screen here is the scope is just randomly scanning and then displaying the scan information. And this is why this waveform I've got, which is a single pulse, so it's a single sinusoid phase once every half second, and you will see it randomly being seen on the screen. Hopefully you've been watching this maybe as I've been talking. Now then, that's not very good in terms of, well, we know there's a signal there, which is actually really important. However, it'd be great if we could actually catch it and see it and examine it. So we're now going to look at the auto. And there's a reason why I've actually just put a single cycle in and using this burst period, of which I'm going to change in a minute from half a second to 2 seconds. But at the moment, let's put it onto auto. So it's auto triggering. And now you will see it is capturing our waveform. And now you will see, because we are triggering, we can actually now choose a trigger source, whether it's from channel A or channel B. We've got a pre-trigger. Now this 50% here, the pre-triggering, is the position on the screen that the actual captured waveform is going to be shown. Now at 50%, it's actually in the midpoint of the screen. If I change this to 40% and wait for the capture, you'll see now it's moved from that point to this point. And so it allows us to see more of the post signal and less of the pre-signal. And I can move this again and put this down to 10%. And now you'll see at 10%, we're just seeing the start of the capture and the remaining period. Now this is interesting. So I'm going to change the bursts here so I can look at this more data. So I'm going to change the number of cycles from 1 to 4. And let's go enter. And so now you'll see it's picked up 4 cycles. So by changing the pre-trigger, it allows me to actually see more of my the post signal. So there's the start of the signal, and then I can see more of it. Now, similarly, you may actually want to examine a signal in more detail to see maybe what happened before a particular event, in which case you can actually change the pre-trigger, and we can change that to 80%, for example. Now you can see I see less of the post signal, but more of the pre-signal, and that can be useful. So this is just to let you know that that's what the pre-trigger does. So I'm going to put this back to 50%. Right. Now then, the threshold voltage, now I know that this signal is going through 0 volts. It's got no offset on it, so I've got a sine wave going positive by 0.5 volts and going negative to 0.5 volts, and therefore I know that so long as my trigger is somewhere between these 2 points, then it will trigger. Okay, but if I go outside of this threshold value, then it will not capture the signal because the trigger is not set up correctly to actually capture that trigger, to capture the signal. So let's see now then. One of the things about auto, and it's not being clearly shown here, is we're capturing this signal that's coming out every half second, and it is great. That's exactly what we want to see. However, auto automatically rearms the triggering mechanism, and that's fine in this particular case, but I want to show you what happens when you actually change the rate at which this signal is actually being issued. So I'm going to reduce this to 1 cycle again first. So I'm going to change this to 1 cycle, and there we are, we picked it up as 1 cycle. But now what I'm going to do is change the burst period to 2 seconds, and let's just put this in 2 seconds. Now what you're going to see now is, because the scope automatically rearms itself, it captures the signal, but then thinks, I haven't had a signal for a while, I'll rearm the triggering mechanism and I'll just run a scan. So it's not necessarily triggering on the event. What it is doing is it can trigger on the event, but it also, if it hasn't had a trigger for a while, it says, oh, I'm going to trigger the scope anyway and catch whatever's there. Hence the reason you see this signal appearing and then disappearing, because that's in reality what's going on, but that's actually maybe not necessarily of great use to us. And this is where normal comes in, because normal will only trigger on the actual signal event, i.e. it's looking for the characteristics that you've set up here, and it's only going to trigger when it sees those conditions. So let me now go to normal here, and now you will see that it's locked the signal, and this is going to update because my signal is being issued once every 2 seconds, and this will update every 2 seconds. So if I've got some random signal event, then rather than losing my screen altogether, which creates, for example, this, in the auto mode, where it just went to a straight line like this, this only captures the event and only displays that, and it won't do anything else until it sees the same event again. Okay, and this is the difference between auto and normal. So that's actually really useful. Now, the thing is that there are times when you might be looking at this signal and you want to examine this signal in detail. But then all of a sudden another signal comes along, and the one you were looking at all of a sudden now changes. And this is not very good. Especially this happens particularly when you're looking at or analyzing protocols, and you want to look at, for example, SPI, which we're going to look at in this video, to show that we can capture events and analyze events before another communications event occurs, because we might be analyzing that signal and thinking, oh, hang on a minute, it's just disappeared and changed because some more data has come out, but it's different from the one I was looking at. And this is where single shot comes in. So what I'm going to do is put this onto single like this, and now you will see it's captured an event, but you'll see in the top left hand side it said stopped, and this means that this will not trigger again until you arm the triggering circuit. Now I'm going to change the number of cycles here to 3 and enter, and now you'll see that nothing's changed on this screen because the triggering circuit has not been armed. As soon as I arm the trigger, it's going to run and it's going to look for the event, and now it's captured the 3 signals, but once again it stopped because it's completed its triggering event and it's not going to change it. And this is essential when you're looking at protocols and analyzing protocols, and you can truly save yourself hours or even days of time trying to work out what your software might be doing when you're trying to look at what's my data format for this, for example, I2C or SPI or UARTs or whatever it is, and you're trying to debug your code, but you don't know what's going wrong. In the case of I squared C, you might be looking for the acknowledgement signal and you can't see it. And it's just a mass of signals, but how do you catch this and analyze into detail? And that's by using single shot triggering. It is so powerful and can save you so much time. It's unbelievable. And I'm going to try and demonstrate all of this because once you get your head around this, it does make Scope so powerful as a bit of test equipment and a bit of analytical equipment, especially when it comes to microcontrollers and embedded systems and all that kind of stuff. Okay, so hopefully that's explained what's going on. I'm going to put this back to 1 cycle just so that we can do this. Once again, it won't change this because I haven't armed it, but if I arm it, then you'll see it's caught it, and there's my single cycle. Now, the thing is that if you go from single shot to any of the other modes, it doesn't matter whether it's none, auto, or normal, then what will happen is, let me just go to auto. Nothing will happen here because once you've been in single shot mode, it does expect you to actually rearm the triggering circuit. And so you have to actually purposely go and rearm the circuit. Once it's rearmed, then we're in auto mode and we'll see our signal dropping in and out like this because we've actually rearmed the circuit and it's in auto mode, and therefore it'll randomly scan as well, because it thinks I haven't had a signal for a while, as I just explained in this earlier on. So let's go back to our presentation. So hopefully that explains the difference between none, auto, normal, and single. So then we've got the triggering edge, of which there's positive and negative. So let's go and go back to our scope here. So what difference does this make? Well, at the moment we've got is set to a falling edge. So what it's doing is it's triggering. So let me just go back to normal here so we actually catch this properly. So this is looking for a transition through 0 going from a positive value to a negative value. And so it'll trigger on the falling edge. If I change this to rising edge, it'll now try and find the signal which is going from through 0 from a negative value to a positive value, hence the reason it's caught at this point in time. Let me just put 2 cycles in here instead. So I'm going to change the number of cycles to 2 and enter, makes it a little bit clearer. So here you can see that it's on rising edge through 0, and so it's going, it can't find it here, so it's going up and then down because that's a negative, that's a falling trigger option. So it's waiting for a rising option, so it's rising here, and that's how it's caught it, and that's the point at which it's going to show us on our screen. Okay, so if I now change this to a falling edge, the first falling event is here, and there once again it's gone up, it's gone down from a positive value through 0, which is our threshold value, and then down here. And of course it won't pick it up there because that's on a rising edge. And if I change the threshold voltage here, just so that you can actually see what's going on, I'm going to change this to 0.2 volts. So let's just put in 0.2, and this is why the voltage is so important. Now you'll see it's picked it up as it's a positive voltage here, but it's a falling edge. So it's going, the signal's going up from 0, it's coming down here, it's caught it as it's coming through 200 millivolts, going in a negative direction, the falling edge, and therefore it's captured it here and displaying it from that point. Similarly, if I change this to minus, or if I do this from a rising edge perspective, just to show you this, let's put it on a rising edge. Now it'll catch it earlier here because it's going from, there's a 200 millivolt point, it's on a rising edge. So the signal starts at 0, coming up through 200 millivolts, going positive, and it's captured it there. If I now go to negative 200 millivolts minus 200 millivolts, and there we go. Let's just get that out of here. So now this is on a rising edge at negative 200 millivolts. Well, the threshold isn't touched at that point because we're below this threshold line here, the 0 volts here, so we're coming up. Going down, it still hasn't found the test condition, even though it's gone through negative 200 millivolts. It's looking for a rising edge, so it carries on through here up, and all of a sudden it meets the condition of rising through minus 200 millivolts and captures it and carries on displaying our signal. And if I do the falling version of that, then you'll see it's picked it up here. So here we've gone up because we've got a negative threshold. It's coming up through, where's the negative threshold? Here it is, and it's on a falling transition, so it has to go through that, going negatively, and hence it picks it up and then displays the pre-signal and the post-signal. So I'm hoping that all of that made sense. Right, okay, in the next part of the video, we're going to look at, let me just go to the presentation here. We're going to look at analog events and how to trigger on analog events. Okay,